application of Ampere's law. So first is the magnetic field due to long current carrying state conductor, due to long current carrying straight conductor. Magnetic field due to long current carrying straight conductor. Suppose this is our straight conductor having current I, this is your long conductor, and due to this we want to make a field, or we want to make a magnetic field at a certain point P. So first point or first step is that making of Amperian loop. That point P distance can be said R from a straight conductor. The first thing is making of Amperian loop. So which type of Amperian loop should be such that which is symmetrical about current carrying conductor. So if we are making a circular loop in such a manner that our conductor passes through the axis of that circle, then the current carrying conductor will be symmetrical like this. See, if we are making a circular loop like this of radius r, then it will be easy because all points on this loop will be symmetrically located from the current carrying conductor. If we want to see the another diagram in another plane, just I am rotating the plane. Right now conductor you are like this and your loop is your like this. If I am rotating the conductor of plane perpendicular, then the conductor will be this and loop will be this. So I am making that plane in the another diagram. So current into the plane. So current in the conductor is like this and it is your inward. So let current here your I, and point P is somewhere here. So this is the Amperian loop. Circular Amperian loop we are getting, and this loop have radius r. That can be said as a circular Amperian loop of radius r. Now, so what is the next step? In the next step, we have to define the direction in which we want to go. So we are going in the clockwise direction. This is our assumption. Okay, we are going clockwise direction. Now, according to our rule, right hand thumb rule, so what we have to do, rotate your finger in the clockwise direction and then see the thumb direction. So all the current which are in the thumb direction will be taken as a positive. See, if we are rotating our finger in the clockwise like this, so our thumb your inward and current is also inward. So I value we have to take first of all clockwise, a positive. Now, as we are going in this side, our element, suppose this is our element dl and we are moving in this side. So our element and our motion both are in the same direction. So angle between V and dl is your 0. So here B dot dl is your mu naught I enclosed according to Ampere's law. So B dl cos 0, that is equal to your mu naught and I. Current here positive because we are moving in the clockwise, current here inward, the current should be taken as a positive I. Now B, dl for whole loop, this is your whole loop, and that loop have total length here 2 pi r, so B into 2 pi r will be mu naught into I, so B is equal to mu naught by 2 pi I by r. This is the magnetic field due to current carrying straight long conductor is same as we have found by using Biot-Savart law. See another example. Okay, now see another application. Magnetic field due to long straight cylindrical conductor of radius r and having current I. Now this is another point here. Magnetic field due to long straight cylindrical conductor of radius r and having current I. It means this is our cylindrical conductor and this have, we can say, up to infinity. This is your long cylindrical conductor of length infinity and its radius is given at r and current here I. So due to this we want to find a magnetic field. So here we are having number of this point. Either we want to find field outside or field on its surface or field inside point. So one by one we will find the field due to all these points, but our basic aim will remain same. Ampere's law, B dot dl is mu naught I enclosed. This is the Ampere's law. So first I would like to find outside point. Field at outside point P, that we can say R is greater than capital R. So again we will make our Amperian loop. So first of all, it is similar type of situation as we found in the previous case in which conductor was your straight. So let our point P is somewhere here and that point is at distance r from the axis of the cylindrical conductor. So when we are making our Amperian loop, so our loop here also your circular Amperian loop. And now we can have diagram in another plane just by rotating our plane by 90 degree. So when we are rotating our plane by 90 degree, so we can have, this is our cylindrical conductor of radius r and point P is somewhere here and this is your distance small r and this is your Amperian loop. This is Amperian loop, which is a circular loop. So after considering Amperian circular loop and current your outward, so when we have rotated the system like this, the current will be over here inward like this. Now next step is that define direction in which we want to move on that loop. Let we are considering clockwise. So when we are moving clockwise by using the right hand thumb rule, according to that, our finger in the clockwise sense, thumb your inward, and our current is also inward, so that current should be taken as a positive. So now we can substitute here. So B into then dl is mu naught into I should be taken here positive. So this will be your B into 2 pi r, your mu naught into I. So B is equal to mu naught by 2 pi into I by r. So this is the outside point, we can write it is your outside. So magnetic field on outside point is given by this relation. Similarly, if we are looking on the surface, field on the surface of this conductor, field on the surface of conductor, it means R is equal to your capital R. It means our point P will be somewhere here. So this is for, this loop is for outside point, Now for surface we can have this type of Amperian loop for surface. If we are looking for surface, the small r will be equal to your capital R. So small r equal to capital R, then the above expression can be written only by changing small r equal to capital R. So B on surface mu naught by 2 pi I by capital R. This is B on surface. So that is for small r equal to capital R, and this is for small r greater than capital R. And now C for inside point. So when we are looking for inside point, field at inside point. Inside point means here small r is less than capital R. So when we are looking for inside point, so see here our point P somewhere here, this. So for this point our Amperian loop will have radius r, but that is your less than capital R. This we can write for inside point. For inside point. So for inside point, if we are making our Amperian loop, see the diagram. This is capital R. So our Amperian loop will be like this. This is your Amperian loop. If this is your Amperian loop, so whatever current associated with this cross section area, that current only we have to consider, because that current will be your enclosed current. So see how to get that value. This term will be remain same. So B inside into 2 pi r, because this circumference is 2 pi r, mu naught. Now the question is that what is your enclosed current? The current which is enclosed by this Amperian loop. So total current I was associated with the cross sectional area pi r square. So current per unit area will be your I by pi r square. This is the current density can be said, current per unit area. Then the current associated with the area of radius r. So this is your pi into a small r square. So now we can simplify B inside mu naught by 2 pi. Pi and pi cancel, 1 r and 1 r cancel here. So this left only I into r by r square. So this is the inside point. So what is the conclusion from these three situations? B outside inversely proportional to distance from the axis of the loop, and B inside directly proportional to, so we can say B outside is inversely proportional to R, while B inside we can say directly proportional to R. If we want to make a graph of variation of magnetic field from the axis of the loop, so our graph will be like this. So let R is the distance from the axis and B is the magnetic field. So first we can say magnetic field is linearly increasing as distance r is your increasing. So linearly increasing means like this, up to the surface. Up to surface means small r is your capital R. After that, outside point here, B is your inversely proportional to R, then it your decreases like this. So here we can write B inversely proportional to R, and here we can write B directly proportional to R like this. So this is the variation of field from the axis to the infinity. So this is another application of Gauss law. By using the Ampere's law, we have determined the magnetic field in all the point, outside point, inside point, and on the surface. Now see the another example or another application. Now see the next one. Magnetic field due to current carrying long cylindrical pipe. So this is the one another application. With the help of Gauss law, we can determine magnetic field easily. This is your pipe, and this is the axis of pipe. Let R is the radius of the pipe. So here in this problem and the previous application, it appears both are similar. Only one difference is there. In the previous example or in the previous application, our conductor was a cylindrical, but that was not pipe. It was conductor. Conductor means the current was from whole of the cross-sectional area. But here our pipe is there, which is hollow from inside. So which is hollow from inside, it means current will be only from the surface part of this. It means from these are the part through which current is there. So I is the current through only surface part. Or if we are making a diagram in that view, so this is the circular conductor. This is your cross-sectional area of the cylindrical conductor, and conductor is your like this. This is your cylinder like this. And if current here, I am considering your upward. Upward means if I am rotating this, it will appear current here goes inside. So these are the cross. in this manner. So here current is your everywhere inward like this. Now due to this we have to find magnetic field. So here also we are having three different position. One your outside, another inside, and third is on its surface. So when we are looking outside point, so first outside point, first your outside point. Outside point means R is greater than capital R. It means if we are looking somewhere here and that point is your at distance R from the axis, now we will make a Amperian loop like this. This is the Amperian loop. And if we are making in this diagram, so our Amperian loop will be like this. And point P is here. If we are moving and current your cross means your inward. If we are moving suppose here in clockwise direction, same method. This is your R, clockwise direction, same method, apply Ampere's law. So here when we are applying Ampere's law, B into 2 pi R and mu naught into I. So B outside will be mu naught by 2 pi I by R. This is the magnetic field on outside point. So this field is similar to the field which we have found in case of cylindrical conductor. Similarly, if we are looking on the surface of pipe, surface of pipe means R is equal to capital R, so no need to do anything extra. Directly we can write by replacing small r equal to capital R I by R. Now third, which is important point here, inside point. Inside point, it means small r is your less than capital R. So when we are looking the field at inside point, so main important point here, if we are making a Amperian loop, right now this is the cross section of our conductor. This is a cross section of our conductor and current is supposed to be, consider your inward. Now for inside point, we will have this type of Gaussian surface, this Amperian loop. Now when we will have this type of your Amperian loop, so what we will find this here. See, current is only on the surface. There is no current enclosed by the surface. So no current enclosed by the surface means net current is 0. So B dot dl will be there, but current is your 0. So since dl is not equal to 0, so what is here 0? B inside is 0. So there is no magnetic field inside the cylindrical pipe. So if we want to make a graph of variation of magnetic field from the axis of the current carrying cylindrical pipe, so we found there is no magnetic field up to the surface. Immediately at surface the field will be there. After that field is your decreasing, and this field is same as here beyond surface. Likewise, so this is the variation of field, magnetic field variation. So outside the cylindrical pipe, it is inversely proportional to position, and B is inversely proportional to R, like this. So this is the variation of field by using Ampere's law. Now see the another example or another application. A long hollow cylindrical pipe of inner radius A and outer radius B, having current I. Find the magnetic field. Find magnetic field at point R. So first part here, R is less than A. In the second part, R is between A to B, and in the third part, R is greater than B. These are the three parts here it is given. So first see what is our this condition. This is your cylindrical pipe is given, hollow cylindrical pipe. It means like this. This is the axis of pipe, and these are the part here through which current is moving. Current here I through this part. So this have radius A and this have radius B. It is given. So if we are making a top view of this, from the top view, this will appear. This is A, this is your B, and current is through this part, and I is the current here. So now if we are looking the field at different point, the first is your R is less than A. See, R is less than A. So now if we are, it means our point is your inside this. Inside this means if we are looking through the cylindrical pipe, our point is here somewhere here P. So our point is here, and this is the distance R. So when we will make our Amperian loop, the Amperian loop will have radius R like this. This is your Amperian loop, and in this diagram, if we are making the Amperian loop, the Amperian loop will be like this. This point P, this radius here R. So this is the Amperian loop like this. So what has been observed from this, current enclosed through the Amperian loop. There is no current through the Amperian loop. So magnetic field, if we are using Ampere's law, according to this, B dot dl mu naught I enclosed. So what has been found, I enclosed is your 0, so B dot dl will be 0. Since integration of phi dl is not equal to 0, so B must be 0, so we can write B inside point 0 in the first part. So if the point is your less than A, it means inside the inner radius, then the magnetic field at that point will be 0. Similarly, if we are looking for the second case is that our R is less than V and greater than A. It means our point is somewhere lying from inner to outer surface, like this. Suppose point P is your this. This is the axis. So this will be our Amperian loop, radius R. If we are making the diagram in this plane, so it will be like this. This is the radius A, this is your outer surface, radius B, and our Amperian loop is like this. This is the Amperian loop of radius R. So when we will calculate the enclosed current, so current will be enclosed only from this part of this part only. So total current was I, which was associated with the cross-sectional area pi b square minus a square, but now our current is only this part. So according to Ampere's law, which is your B dot dl, your mu naught I enclosed, so we can write here B into 2 pi r mu naught. Main point is the calculation of I enclosed. Current enclosed means current through this part. So current per unit area will be your I by pi b square minus a square. This is the current per unit area, and then the area of this part, your pi r square minus a square. So finally we will have B is equal to your mu naught by 2 pi r into I r square minus a square by b square minus a square. This is the second part, this one. Now if we are looking the third part, in the third part, see, if we are looking the third part, when R is greater than B, when R is greater than B, it means our point is somewhere here, and that point distance here R from the axis of the conductor. So for this, if we are making a Amperian loop, so Amperian loop will be like this. So here whatever the I induce or enclose, that will be total current will be. So B into 2 pi r mu naught into I. So B for outside we can say mu naught by 2 pi I by r. This is the net magnetic field. So in this manner we can get the field. For first case, R is less than A. For second, R is between the inner and outer surface. And third is your when outside point is there. Now come to the next application. Now see the next application. Magnetic field due to magnetic field on the axis of long current carrying solenoid on the axis of long current carrying solenoid. Now, in case of long current carrying solenoid, let this is the solenoid. In the long current carrying solenoid, our conditions are that first of all, R is very small as compared to L, and if I is the current, so what we have found, if we are making a cross-sectional view, so in cross-sectional view, this type of current carrying conductor we will find. This is the one of the wire, another wire is like this type of number of, you can see, and these all are indicating one of the loop like this. So if current is your I here, this is the current, this is the current like this, each have current here I. It means this type of, I am talking about like this type of loops are there. So if I am looking at this junction, so current will appear coming out, and here current is going in. So coming out means we can say this is your dot indicate current is your coming out, and it enter here, it means it goes out inside, current is your out like this. After that, how to calculate, and this thing will continue. Let up to infinity means practically not infinity. This is the situation prevailed. Each loop have current your I. Now I am making the Amperian loop. So here I am making the Amperian loop like this. This is the Amperian loop. Let A, B, C, D is the Amperian loop, and it has been found the magnetic field due to this current. If I am looking, see the dot upward current here, magnetic field lines, if I am looking here, so like this. So magnetic field direction here this, but here field is your outside, this is 0 like this. So now, according to Ampere's law, B dot dl is equal to mu naught I enclosed. So when we are calculating total B dot dl, so that is nothing B dot dl from A to B. Let we are moving like this, in this manner. So A to D, then B dot dl, D to C, then B dot dl, C to B, then again B dot dl, B to A. Now, when we are looking from A to D, magnetic field here along the axis of the loop, first of all, in the outside of the solenoid, there is no magnetic field, so here B dot dl will be a 0. And if I am looking the inside part we are going in this direction, but magnetic field here in this direction. So angle between the B and dl here 90 degree, so B dot dl will be here 0. So this term becomes here 0 plus. When we are looking from D to C, D to C means in this. Our arrow direction is like this also, and we are moving also D to C. So angle between B and DL here 0. So cos 0 will be your 1. So it become your B into L plus. As we are looking from C to B, again the same situation as we have found from A to D, this value will be also 0, and plus B to A, outside the magnetic field is 0, this term is 0. So finally we are getting here B dot dl is nothing, it is your B into L. Now from Ampere's law, BL is equal to mu naught I enclosed. Now what is I enclosed? Mu naught I enclosed means current due to all these conductors. Let we can write here N is the number of turns per unit length into L into I. This is your B into L. So B is equal to your mu naught Ni. So where we can write N is a number of turns per unit length. So in this manner, by using Ampere's law, easily we can determine magnetic field on the axis of long current carrying solenoid. Similarly, see another application. Now magnetic field on the axis of a toroid. Now suppose by using Ampere's law we want to find magnetic field on the axis of toroid. See, in this manner we can get. First see the toroid. In the toroid, a wire has been wrapped in a circular support like this. If I is the current here, and this is called your axis, and this axis we can assume as an Amperian loop also. R is the radius. So here this is taken as a Amperian loop. This is taken as a Amperian loop. Now according to Ampere's law, B dot dl your mu naught I enclosed. So now if we are looking the magnetic field here, let we are moving clockwise. So we can write here B dot dl mu naught and I enclose. I enclose means let total number of turns in the loop is your N. So current through one loop your N into I, where we can write here N is the number of turns in the toroid. Number of turns in the toroid. So this further written as B into 2 pi r mu naught N into I. So B on the axis written as mu naught N by 2 pi r into I. If we want this expression further written as mu naught N into I. So where N can be said as a total number of turn by circumference or length of toroid. This is further written as number of turns per unit length. Number of turns per unit length. In this manner we can express the field on the axis of a toroid. So these are the few application of Ampere's law, and by using the Ampere's law it is easy to calculate magnetic field on a highly symmetrical location. Highly symmetrical location means the current distribution about that point is symmetrically distributed.